Okay, let's start our lectures in this semester. And informal title of this course uh, is following. This is Introduction to Stochastic Analysis. It naturally continue the course of a previous semester, which was devoted to infinite dimensional probability distribution. Today we will speak about the aims and reasons which leads to the question of our course. The name is stochastic analysis. Maybe you recall your first student years where you had the course which is called mathematical analysis or simply calculus. It depends on the university. And what it is, the main object of investigation in this course. The object of investigation were functions, which are defined on the finite dimensional spaces. And we studied a lot of properties of functions, defining the limits, derivatives, and differential forms related to different vector fields and so on. So the main idea of the course of calculus was that we can define some infinitesimal characteristics of functions like derivative, which is most known and most important, and then using properties of this infinitesimal characteristic, uh, give the answer on the questions about the behavior of the initial function, or about the shape of the graph of this function, about existence of the maxima, and so on. It was extremely useful to have the derivative or higher derivatives of some functions. Now let's back to probability theory. And maybe again from the first, excuse me. У меня сейчас лекция, а потом первая. Maybe from the first lectures on probability theory, you can remember that in the classic probability theory, we don't need any assumption about probability space. We can just think about the discrete random variables, defined expectation, variance, and a lot of good things. Define the independence property and so on. But after we jump to the formal theory, we give such a definition. What is the random variable? Random variable is a function defined on probability space and taking values in R or in RD or somewhere else. So we have in mind already the idea that one can consider a random variable as a function. And actually, this course is devoted to the development of this idea and to development of the tools which will be similar, but from other side more complicated as in calculus, and which allows us to study random variables as a functions. So let us consider some motivating reasons how we can jump to this to this study. The first one was related to the central limit. Everybody knows that if we consider the sequence of independent, identically distributed random variables, even suppose that they are discrete. From the we are taking these variables from the classical probability theory. Then we will have some finite set of values, related probabilities, and when discussing expectation, for example, we don't need any probability space. We just say that it is equal to the sum from k equal 1 to m, ak to k, value and probability, value and probability. But after we have such a simple picture, it occurs that if we define sigma as a variance of psi n, then the following interesting relation holds. It was discovered that probability that Sn minus expectation of Sn divided by square root of n sigma less or equal than x tends to integral from minus infinity to x 1 over square root of pi e minus u squared to du when n tends to infinity. Here, as usual, Sn is a sum of psi 1 plus psi. It is not hard to check that the integral from this function is equal to 1, and it is desired to interpret this integral as a probability related to some random variable. So, on this stage, it was good to have such random variable, that probability that psi is less or equal than x is exactly this integral from minus infinity to x 1 over square root of pi e minus u squared to d. We already immediately have a question. Where this random variable can be defined? Because if those at least finite number of those discrete random variables can be defined on very simple probability space, we just can say that we have a finite number of events and so on. But when we want to define such random variable, we cannot have discrete probability space. Of course, if you are following carefully to my arguments, you already have a problem because the IID sequence cannot be defined on the discrete probability space. But when we discuss this expression, we need only finite number of this expression. Here, the situation is opposite, and we need probability space. We need probability space. I think that everybody understands that, for example, universal probability space like omega equal like omega equal 0, 1, F equal Borel sigma field, and P is equal to the big measure, is good. And it is easy to define such random variable on this probability space, which has such distribution. But this choice seems to be artificial, and construction of this random variable is not very not looks like it came from the experiment. So let me propose to you another choice, which is at least more easy and more natural in this case. One can consider, instead of this universal space, one can consider such choice. Omega is equal to R, and F is again a Borel sigma field, and the measure P is defined with this density itself. So P of a set of some interval E is equal to the integral over E of this function. 1 square root pi E minus U square 2 du, and then it is easy to have this random variable. We can just define psi of omega equal to omega. We do not need some special construction. Yes, if we did it in following way, we exactly will have this property. It's evident. Moreover, this construction has one interesting advantage. Let's see. Suppose that we want to discuss some other random variables which are defined on this space. Then one can say that if we have eta, now it must be a function from omega to r. Moreover, it must be measured function. We know this. So it is a function, and we have the correspondence omega, which belongs to our r, eta of omega, but you remember this equation. So it is eta from psi omega, where psi is initial random variable. We know that it has standard normal distribution. In this way, I even can put here another symbol. Let me do it just erasing old ones, and I will put here F. So what we did, we associate with this new random variable eta, we associate function f. So we have such three objects now. We have initial psi, which is Gaussian standard random variable. We have random variable eta, and we know that eta is represented by f of f from psi. Now, because of we mentioned calculus or analysis in deterministic sense in the beginning of the lecture, and see here function f, one can imagine that maybe now after this construction, one can think about the such differentiability. You see, we are speaking about differentiability of random variables of eta. And it occurs that this is not just artificial question. For example, let me show you the usefulness of such question. Suppose that the function f suppose that function f is such that f is strongly increasing and f is from C01 on R and f prime is greater than 0. Then one can say that eta has density. Immediately it follows from this that eta has density. Then eta has density. Moreover, we can find the expression of this density very easy by change of variance formula. One can check that the new density Q of x is equal to 1 square root of 2 pi e minus, here is f minus 1 x squared over 2 and multiply 1 over f prime and f minus 1 x. So here is a density. And knowing the estimation for f prime, one can even have good estimation for the density Q. You already have courses in mathematical statistics and know that knowing of properties of density is extremely useful. For example, we compute with this using this knowledge, one can build confidence intervals and so on. So you see, very simple calculus leads to the useful expression and useful conclusions in probability theory when we have representation of our random variable eta as a function of a random variable x. Of course, this example looks very simple because we have only one variable xi, and it must be much more developed. It occurs that it can be done when applying to stochastic differential equations. I just shortly will say about this because we will detailedly discuss it further. But I want to just give you an idea of what we will do. So instead of this Gaussian random variable xi, let us consider well-known for everybody of you Gaussian process, which is a source of randomness in usual dynamical system model construction. This is a Wiener. So instead of xi, I will consider W t, for example, when t is from the interval 0, 1, and I will suppose that T is a standard linear process. This object, by the way, arise, and we will recall this, also due to the central limit theorem as a scaling limit of the symmetric envelopes. So we have such a Gaussian process, and using this process, one can consider such analog of differential equation, which is widely distributed as a mathematical model for random motion under the random perturbation. So it looks like this. We have a usual term related to the ordinary differential equation plus the next term, which can be formally written as follows. Here, the differential with respect to W must be understood in special way, and there is a special construction of this integral, so called Ito integral, and A here is responsible for the external forces which are acting on our system with the position xt, and B xt dw is responsible for the influence of the random media on our system. And it occurs that in this case, of course, xt is functional from W. Why I am saying functional? Because from the previous semester, we understand that W is a random element, in the space of continuous functions. We remember that it has continuous trajectories. So one can say that now our solution X is a function of W. So xt is some function. Let me continue using this small f from W. W as an element, not W with in some point, but as element here. It depends on the trajectory, and of course, here f dot t is acted from C01 as a Banach space to R. Yeah? Of course, now picture looks more complicated as before, because we have a function which is defined not on the R1 or on the finite dimensional space, but we have a function which is defined on this infinitely dimensional and very bad Banach space. We mentioned this last semester. So this object is much more complicated, but still it is a function. And when we have this expression, we can forget about probability sense of it. And one can try to use the same approach. Let us look for good properties of this function. For example, maybe, I don't know, but now I don't know, maybe it is differentiable. And maybe then one can apply change of variables formula to the distribution of W, which is defined on infinite dimensional space, and then get the conclusion that xt has a density. It looks like a complicated way. It looks like a complicated way because, again, it is infinite dimensional space. Here, the distribution of W is just a Gaussian measure in this space. So we have to check differentiability. We have to look for change of variables formula. We have to look for conditions for a good answer in this existence, in this change of variables formula, and so on. So there are a lot of technical details. And somebody can say, oh, it's very boring way. Why we have to look for the density of xt in such a complicated way? But let me reformulate the problem. And
can I ask a question?
Exactly.
Yeah, so I don't really understand because you write xt as a function of the Wiener process and t, right?
Yes.
But it also depends on xt because xt is the solution to a different SDE. Isn't that like a problem?
This xt is a function. Maybe you want to put here initial condition.
Yeah, something like that. But because it is weird that it only it is weird that it depends not only on the Wiener process, but it depends on itself as well as a solution to SDE.
No, this is not the right idea. Here is a way. Yes. Suppose that you see. Suppose the coefficients are good. Let me just briefly recall you a usual schema. How we define the solution, how we get the solution. Suppose that there are ellipses, then we are constructing this successful approximations. Yeah, x is like x0 plus integral from 0 to t a n s ds plus integral from 0 to t.
Okay. So the right-hand side is then a function of w, and then you take the limits and see and look at this. Okay, okay, that is the idea. Okay, thank you.
No problem. So we have, but thank you for the question. When discussing this question, we understood that this f is a really complicated thing. Yeah, this is a good point. It is a really complicated thing. And as I'm repeating that one can say, oh, it's not a good way just discuss the existence of the density. But let me recall you, and you will see this maybe in the lectures of Nikolai Ivanovich Portenko, that density of xt, if it exists, suppose that we have density, xt has density q t, it depends on x0 and from u. It is a fundamental solution. It's a fundamental solution. To the following partial differential equation related to our one. Here is equation like this one. D u capital is equal 1/2 of a square x d2 dx square u plus b oh, excuse me, here is b and here is a plus a of x b squared a of x du dx. You see? So you have a parabolic equation with non-constant coefficients. And the equation of existence of the density is related to the existence, to the equation of the existence of good fundamental solution to this equation. Yeah. Moreover, I wrote here just one-dimensional case because of the small point. But the same happened if we consider multi-dimensional case with multi-dimensional W, with multi-dimensional Wiener process. Then the equation of existence of the good fundamental solution became to be very complicated. If we continue to study this question based on the deterministic theory of parabolic equation, we will look very heavy difficulties, and it was a well-known theorem of Hermander, Lars Hermander, about hypoellipticity. He introduced conditions of hypoellipticity for coefficients of parabolic equation, under which we have good fundamental solution. But the theory is very heavy. And it was very interesting that exactly after his invention, Bismuth and then Malliavin introduced this probability approach, which we mentioned briefly now, based on the investigation of xt as a function of the W, investigation of the differentiability properties of this function, and finally, they give the same condition of hyperellipticity, but in very clear and efficient way, which we can use the arguments in very different construction. So it occurs that this way, which I mentioned, is at least shorter than the strict way of Lars Hermander based on the theory of deterministic parabolic equation. This is one source of our of the equation of our. So we just have seen that maybe the consideration of random variables or random vectors like a functions from the Gaussian process, it does not matter W or something else, will lead us to developing of differentiability of such random variables and to some conclusions about existence of the density of this random variables and estimation of density. Another source came from extremely different problem. And when it arose, it was like 70s of the previous century. It looks like it is very different. Let me recall you the framework of stochastic differential equation again. We say that A is responsible for the external forces which are acting on the system. And we understand very clear what is the influence of properties of A on the properties of solution and so on. This term is responsible for acting of the random media at the time t. And when discussing the formal expression, when discussing the formal theory of such stochastic differential equation, we need to understand the integral here and the Ito construction was the following. We just introduced the past of the Wiener process. So this is a sigma field, which is generated by the values of Wiener process up to moment t. And one can consider Ft like all events which we can determine when consider our noise up to the moment. Since we have a dynamical system under influence of our noise, it is very natural to say that Xt is measured with respect to F. So when we are even suppose that we have this differential equation which comes from stochastic finance, yeah, then when we are discussing the change of the exchange course of some currency, then we don't care about the fluctuations which will happen after a year of this day. So we don't care about the future. And so it is a very natural condition. And using this condition, one can construct the Ito integral which is involved here. Here is bxs dws. Such theory of stochastic differential equation was developed here in Kiev by two well-known and great mathematicians of previous century, by Gihman and Skorokhod. And it is interesting that Skorokhod was one of the first person who introduced another framework. Let me ask you, what will happen if we want to consider not a dynamical system, but string under the random fluctuation? Suppose that we want to consider a string under random perturbation. So one can remember that if we consider a string, then we don't have time. We just have the interval, for example, 0, 1, and here we have fixed points, and here we have our string. Yeah? And if we say that we have attitude and at the point say x and t here, then maybe one can say that we must have this attitude is equal to u capital. This is equation for the string dx dt square is equal d2 u dx square plus, and here are some fluctuations, yeah? Plus psi xt plus psi xt. And if we consider here just simple fluctuations, then it is not very hard to construct the solution. We just can define this psi as a formal derivative of Gaussian measure with independent increments in x and t and so on. But if you want to put here, put here u or some function of u, so-called multiplicative noise, then it becomes to be difficult because we have fixed points. We know something about our solution, not only at the point 0, but also at the point 1. So such kind of problems naturally leads to the following question. What happens if we consider usual stochastic differential equation dxt equal a xt dt plus b xt dwt, and here we have initial condition. But suppose that this initial condition, like zeta, is measured only with respect to f1. Then, in which sense we can define this integral? And Stochastic was able to define it, and it was named by his name. Now it is known like Stochastic integral. Sometimes he did not use his name when discussing this integral, so he used the term extended integral. Sometimes we say extended integral, and it occurs that the solution does not exist in general. Why? Again, it occurs that one can consider this stochastic integral, as now this integral is differential operator. On C01. So you can imagine that when we consider this function xt, this random variable xt as a function on this space, we get partial differential equation for this function. And since it is nonlinear, it in general, as usual, in deterministic theory of partial nonlinear differential equation, it has not a solution on all line or time interval. So the solution of such problems can be studied using again differential calculus for functions from C01 to R with the Gaussian measure, with Wiener measure on this space. So you see this problem of anticipating equation. It is named like this. Leads us again to the same tools. We need to study some functions on the space with Gaussian measure. This is another source of our investigation. And the last one, but not the last of the importance, is quantum physics. Why? Let me recall the very natural approach to discussing derivatives when we have a Fourier series. Exactly. If we have a function f of u, which looks like a sum from k equal 0 to infinity, ak sine k u plus dk cosine ku. So we have a Fourier series, good Fourier series. Then its derivative can be obtained like this. The sum from k equals 0 to infinity, k ak cosine ku minus k dk sine. Yes. So under good conditions on the coefficients, namely sum of squares k0 to infinity, k square ak square plus k square bk square is less than infinity. Then one can say that at least in square mean, in two sense, f has a derivative, and derivative has such an expression. So you see why this approach to discussing of derivatives is interesting for us. We imagine we will have functions on infinitely dimensional space. So there are very big technical difficulties when one can try to define derivatives of such function. For example, you remember from the course of functional analysis, Hatung derivative, Frechet derivative, weak derivative, and so on. Yeah? A lot of notions, and which one will work, we don't know. Also, you can imagine you just have a random variables with some properties. Yeah, we know that it is measured with respect to xi, with respect to our w from C01. But how to define this random variable in fixed point in order to apply this Frechet theory is a difficult question. So maybe such approach can be useful. Yeah? But we have to invent something instead of this Fourier series. So one can try to look at the expression when we have eta, which is function of w, maybe eta can be expressed again like a Fourier series in terms of some orthogonal expansion. It occurs that it is true, and we will discuss this very detailedly. And it is interesting that again, completely different guys, Cameron and Martin, they were working in functional analysis, discovered this construction. So you see, we mentioned different sources today, which leads to rising of stochastic analysis, and very different people fixes. So we consider they invented that one can put here some. Let me denote it by this. From W. These are like polynomials for Wiener process. Moreover, every such polynomial can be associated. We will discuss it. Now we just discuss motivation. Can be associated with a function which belongs to L2. For example, here 0, 1, but to be more close to the quantum physics, suppose R in K power and symmetric with respect to all variables. And then one can check properties of eta in terms of these kernels. Moreover, when one can define stochastic derivative of eta, the corresponding kernel will be like AK, and here we just take dot, and other variables remain the same, so it belongs to A2 K minus 1. So we will have very good kernels representation for eta, like Fourier representation for periodic functions, and we can discuss the derivatives in sense of this expansion. But, and it was discovered again by other people. It was discovered by Siegel that there is an object in quantum physics exactly like this series. We can consider so-called Fock space. Fock space, which is defined as a Fock space, which is defined as a orthogonal sum from K equals 0 to infinity. Here is L2 RK symmetric, and this Fock space is responsible for the wave functions of the system of bosons because of symmetry here, with change of number. You see K can vary here from 0 to infinity, and it occurs that such operator of derivative here is related to operator of annihilation of particles. We just kill one particle, yeah? We just kill one particle. And a joint operator, which is an operator of creation of particles in physics, is exactly extended integral, which we mentioned before, is exactly a Stochastic integral. So we have a very strong connection with quantum physics here. And this connection, of course, is much more deep than I mentioned. From this point of view, we already discussed today 3 motivating sources for our course. We will do the investigation of random variables as a functions of a Gaussian random element in some Banach space. Doing this, we will get Malliavin condition for high elasticity. We will get the solution to anticipated stochastic differential equation. We will discuss the second quantization method and discuss the relation between Lagrange equation and Schrödinger equation for wave functions. This is a plan of our lectures for this semester. Today, that's all. Thank you for attention. Maybe somebody have questions. Okay, if there are no questions, thank you. And just about seminar, the seminar will be today at my 4.